In the last class, we have talked about Compton effect. And before we understand Compton effect, we have said that whenever any electromagnetic wave of any frequency or wavelength interacts with any type of matter, then the emitted wave has the same frequency or wavelength as that of the incident electromagnetic wave. And that is experimentally verified, experimentally observed that whenever an electromagnetic wave like light of any frequency or wavelength interacts with any type of matter, then the emitted wave shows same frequency or wavelength as that of the incident wave. But after the discovery of Compton effect, it is theoretically as well as experimentally shown that if you use an electromagnetic wave of smaller wavelength, if you use electromagnetic wave of smaller wavelength like X-ray, and you take any light element like carbon, then when this X-ray interacts with this light element, then we observe a different frequency or wavelength of the emitted electromagnetic wave or emitted X-ray, and we call that phenomena as Compton effect. So basically, when we are not using light element or we are not using electromagnetic wave of smaller wavelength, then we observe that emitted wave shows same frequency or wavelength as that of the incident wave. That means the wavelength or frequency of the emitted wave is not modified. It is unmodified with respect to the initial wave or incident wave. So these are called unmodified lines. So whenever we observe same wavelength or frequency with respect to the incident wave, we call it as unmodified lines, unmodified frequency, unmodified wavelength. On the other hand, due to Compton effect, the frequency changes or wavelength changes, and with the help of quantum mechanics only, we could explain the reason. And for that, what we have done, we considered initial photon of particular energy, say h nu, and momentum h nu by c interacts with a stationary electron with the energy, less mass energy, and momentum 0. And after the interaction, after the scattering process, we assume the photon goes along theta direction, whereas electron goes along phi direction. And then we also said the energy and momentum of the scattered photon and the electron. And from the energy conservation and momentum conservation, along x and y direction, we have estimated the change in frequency or change in wavelength. So we observe that if nu is the frequency of the incident wave and nu dash is assumed to be the frequency of the scattered photon, then they are not same. 1 by nu minus 1 by nu dash minus 1 by nu has a value. In simpler way, if we replace it in terms of wavelength, we observe that there is a change in wavelength. There is a wavelength shift. Which we call as Compton shift, which is equal to h by m naught c 1 minus cos theta. H is Planck's constant, c velocity of light in free space, so they are universal constant. M naught is the mass of that particle. So if we are using electron, m naught will be the mass of electron, and we know mass of electron is 9.1 into 10 minus 31 kg. So if we put those values, we get the quantity h by m naught c as 0.02427 angstrom. And I have asked you to remember this value for numerical calculations. So if you are using electron as your particle, then lambda c will become this, and this lambda c is called Compton wavelength because its dimension is same as the dimension of wavelength. Now 1 minus cos theta can also be written as twice sine square theta by 2. Therefore, we can write it as twice lambda c. Lambda c is h by m naught c sine square theta by 2. So anyway, you can write it. Either you can write it in form of 1 minus cos theta or in terms of twice sine square theta by 2. Whatever you prefer. Now the point is This shift, that means the change in wavelength, or if I say the scattered wavelength, that will be lambda plus delta lambda, that means twice lambda c sine square theta by 2, or if you just want to write in this way also, lambda plus lambda c 1 minus cos theta, whatever you prefer. Now, whether you are measuring the shift delta lambda or you are measuring the new wavelength, you observe the new wavelength is increased because you are adding some quantity with lambda. You are adding a positive quantity. You are adding this positive quantity with lambda. Therefore, lambda dash must be greater than lambda. So, due to Compton effect, the wavelength of the scattered photon increases. Wavelength of the scattered photon increases. And what is that amount of increment? The amount of increment depends on the angle theta. It only depends on the angle of scattering. It depends only on the angle of scattering. If you remember, that was the initial direction of photon. After the scattering, it goes along a direction, any arbitrary direction, that is theta. So it depends that how much Compton shift will occur depends only on this quantity theta. Because for all the other quantities are constant when the particle is constant. That means if you are considering Compton shift for electron, then h by m dot c is constant. If you are considering it for proton, this value is constant. And that's why we have observed that for different values of theta, we get different amount of delta lambda, and the minimum value will be 0. That means when we say there is no Compton shift occurs, when theta is 90 degree, then shift is equal to Compton wavelength, and shift will be maximum as twice lambda c when the angle is 180 degree. So if you are not considering this angle, apart from this theta equal to 0, for any other angle, you observe Compton shift occurs. There will be a change in wavelength. Maybe the change is very, very small, but there is a change in wavelength. And the new wavelength, the new frequency, the new lines we get are called modified lines. In Canvas, I have already uploaded the practice materials and study materials. That means the brief note is given in your Canvas. Along with that, all types of theoretical and numerical problems that can be asked from Compton effect are given in the practice material. Even for last 15 years, all the questions that came in university paper are given there. So you go through them. If you have any problem, and you will observe that for the same answer, there are multiple type of questions. These type of questions are given so that you can understand what type of question can be asked. Maybe the answer will be same. Go through them. If you have problem in understanding any question, mark it and ask me in the class. Now the point is that you will observe in that practice material, there are so many questions on modified and unmodified lines. What are the origin of modified lines? What are the origin of unmodified lines? That type of questions. So modified line means due to Compton effect, we get this wavelength shift. The wavelength shift depends on the angle. So apart from theta equals to 0, for any other angle, there is a shift. There is a value of delta lambda. And whenever there is a value of delta lambda, lambda dash, which is equals to lambda plus delta lambda, will be greater than lambda. This new wavelength is called modified wavelength. So this is the origin of modified lines. So due to Compton shift, we are getting the modified lines. That means we are getting some new wavelength. Some new wavelengths, why I am saying? Because for different angles, you are getting different value of lambda dash. Lambda dash depends on angle. Lambda dash depends on the scattering angle. So if you change this angle, you will get different values of lambda dash. Clear? Now, let us observe the experiment done by Compton himself. So as I have mentioned earlier, he has used X-ray. Actually, he has used a particular type of X-ray, which is called K alpha X-ray. If you remember your 10+2 standards, there was K alpha, K beta, L alpha, L beta, this type of X-rays. So he has used K alpha X-ray, whose wavelength is 0.709 angstrom. So that is your lambda value. Wavelength of the incident X-ray. And used a block of carbon. And measured the wavelength of the scattered X-ray at different angle. So when the angle is 0, that means when theta equals to 0 degree, it is expected that delta lambda will be 0. So we are getting only one wavelength. This wavelength corresponds to lambda. That is 0.709 angstrom. So this is your 0.709 angstrom. Now when the angle is changed, to 45 degree. When the angle is changed to 45 degree, then if I use the Compton shift formula, lambda dash equals to lambda plus lambda c 1 minus cos theta. If I put the values of theta equals to 45 degree, lambda c we know for electron 0.02427 angstrom, put the values, you will get lambda dash equals to this. It is written in nanometer. That means it will be 0.715 angstrom. In angstrom it is 0.715. So you observe wavelength increases from 709 to 715 angstrom. Expected, that we can expect. But the point is, apart from this lambda is observed at this peak. You observe, and there is another peak. This peak is observed at lambda equals to 0.709 angstrom. What is the reason of it? That means this is the initial one, unmodified line. This is the unmodified line. This is the modified line, which is expected. Due to Compton effect, when the angle is not 0, we should get a different value of lambda. Of course, lambda dash equals to lambda plus lambda c 1 minus cos theta. So theta is changed, we should get a different value of lambda dash. And if I increase angle to 90 degree, lambda dash is increased more. Now it is 0.731 angstrom. Now it is 0.731 angstrom. Increase more. But again you get another peak at lambda. Lambda means again 0.709 angstrom. Why are you getting these values? In fact, when it is increased to 135 degree, then also lambda dash is increased more, 0.749 angstrom. But again, we get a value of lambda 0.709 angstrom. That means we are getting two peaks. Two peaks means we are getting two wavelengths. Experimentally, we are observing two wavelengths, not a single wavelength. Only at theta equal to 0, we are getting a single wavelength. Because at 0, we know there is no Compton shift. But in all the other angles, in all the other cases, we are getting some values. Can anyone tell me the reason? Why do you think we are observing this 0.709 angstrom? Higher value of lambda is expected from the formula of Compton shift, from this formula. But what about this value? Why you are again getting this value? Wavelength increases, no problem. But why you are getting the same value of wavelength as the initial one, as the incident photon has? Any guess? Any logical explanation? I'm giving you a hint. The explanation is not different from our discussion. Whatever we have discussed, from that you can answer it. No attempt.
So due to the as the external legs becomes later same angle as the initial.
Why you are getting the same value of lambda? Unmodified and modified. So you are getting both.
So because sir, the extra plates later get the same angle theta, the same phase.
No, we are changing the angle. Here the angle is not 0. It is 45 degree. Here it is 90 degree. Here it is 135 degree. Angle has been changed. And when the angle is changed, then according to this formula, lambda should be changed. Lambda dash should be changed. Lambda dash is now lambda plus lambda c1 minus cos theta. So it hasn't changed. That's why you are getting these values: 0.715 angstrom, 0.731 angstrom, etc. My point is why we are still getting 0.709 angstrom. Why this wavelength again come?
Yes, sir. Yes, sir.
Okay, I'm explaining it. The point is, in the derivation, we have assumed that the X-ray is interacting with a single electron. The X-ray is interacting with a single electron. Now think practically. Can you extract a single electron from carbon and place it in front of a light beam? Is it possible?
No.
What you can do? You can extract you can take a very small part of carbon. That means you can take a very small portion of the carbon material, but whatever small portion you take, it will consist of several atoms, several electrons. So you cannot actually isolate it. You are not isolating a single electron. Rather, whenever you are exposing that carbon in front of the X-ray beam, you are actually supplying a large number of atoms along with a large number of electrons, not a single one. So whenever the X-ray, when the X-ray photons interact with the electrons, when the X-ray photons interact with the electrons, then we get the Compton shift as lambda dash equals to lambda plus, I'm writing the basic formula, m naught c 1 minus cos theta. And for electron, m naught is 9.1 10 to the minus 31, and as a result you get this value as 0.02427 angstrom, and that's why lambda becomes these values. But whenever the X-ray photons are interacting with the carbon atoms itself, because as I have said, you cannot extract a single electron. So whenever you want some electron to interact with the photons, some atoms are also interacting with those photons. And whenever the atom is interacting, then according to this formula, this m naught is not 9.1 10 to the minus 31 kg. It will be increased 10 to the power 4 times at least, because mass of proton is 10 to the minus 27. Mass of neutrons is of the order of 10 to the minus 27. Therefore, the mass of the atom will be at least increased by 10 to the power 4 times. Therefore, this quantity h by m naught c will be decreased to 10 to the minus 4 times. That means this will be of the order of 10 to the minus 6 angstrom. 10 to the minus 6 angstrom. So it is so small. It is so small that experimentally we are observing that lambda remains same. Because think, it is lambda was 0.709 angstrom. Now if you add 10 to the minus 6 angstrom with it, theoretically lambda changes. Theoretically wavelength changes. But experimentally, practically, can you observe it? What you will observe? 0.70900 something. With the help of any physical instrument, you cannot detect this change. Therefore, you are thinking lambda doesn't change here. So this is the reason. Along with these modified lines, you are getting some unmodified lines. So in nutshell, due to interaction of electrons with photons, you are getting modified lines where wavelength is changed. And when atoms interact with the photons, we get unmodified lines. Then also wavelength changes, but the change is so small that hardly it can be detected. We cannot detect it by our instrument. That's why practically wavelength doesn't change whenever the whole atom interacts with the photon. So this is the reason of origin of modified and unmodified. So theoretically, in both cases, wavelength changes, but when electron interacts, the change is measurable. Whereas when the atom interacts with the photon, then the change is so small that we cannot measure it. And that's why we are getting the unmodified wavelength, unmodified lines. Okay. Next, we'll determine energy of the scattered radiation. What we have observed before. Okay, understand the question. Question is energy of the scattered radiation. Scattered radiation means after the interaction, we get some photon. That means this is the initial photon. After the interaction with the electron or the atom, the photon goes along some direction, say, and in an angle theta. Now we want what is the energy of this photon? Energy of the scattered radiation, energy of the scattered photon that we require. Now, energy of the scattered photon means we require actually h nu dash. H is constant, so basically we require nu dash. What is the value of nu dash? In Compton effect, whenever you do the numericals, remember, or for any practical perspective, remember what are the given thing to you. Given is what material you are using, whether it is carbon or carbon atom, carbon electron, what is the particle. Second thing, which type of electromagnetic wave you are using. That means what is the wavelength or frequency of the photon? What is the wavelength or frequency of the electromagnetic wave? These are the known, and what is the angle of scattering. So basically, either you know nu or wavelength of the incident wave, you know the angle of scattering, and what type of particle you are using. These are the given data always, whether you are doing the numerical or you are doing the practical. Okay, so if you are asked to find out nu dash, that means we need to find out nu dash in terms of this thing. Our variable is theta and the wavelength or frequency of the incident wave. So we will rewrite nu dash in terms of those things. That is the basic thing. And I told you to remember those two formulas of Compton sheet, one in terms of frequency and in terms of wavelength. Basic thing, they are almost same. In case of lambda formula, it is h by m naught c, 1 minus cos theta, whereas in terms of frequency formula, it is c square. That is the basic difference. And wavelength and frequency are inversely proportional, so 1 by nu dash instead of nu dash. So 1 by nu dash minus 1 by nu is this. So from that, what we require, we need to find out nu. Simple calculation. So nu 1 by nu dash will be 1 by nu plus this quantity. Therefore, nu dash will be just take the inverse 1 by this. I require nu dash. How will I get it? Just take inverse of this quantity. So inverse of this quantity. So this is our nu dash. This is our nu dash. That means frequency of the emitted photon. Don't worry, you need not to remember it. But our question is energy. So energy means h nu dash. So we'll multiply h on numerator and denominator. So we are multiplying, sorry, not numerator, denominator. We are multiplying h only. So that h is multiplied with the numerator. Denominator remains same. Denominator remains same. So this is our energy of the scattered radiation. Or we can simplify it more. Multiplying nu in numerator and denominator. If I multiply nu in numerator and denominator will be h nu, and denominator 1 by nu into nu, so 1 plus h nu by m naught c square, 1 minus cos theta. Why I am writing in this form? Because instead of nu, if I say h nu, that means energy of the incident photon. So here we are expressing it in terms of energy of the incident photon. So if you are asked that find out the energy of the scattered radiation, then this will be your approach. You need to first find out the expression of nu from the basic formula. Then you just need to multiply h with it. That's all. You may or may not simplify it. It's up to you. But you need not to remember it, and you will not remember it, because if numerical problems come, we will use some different approach. Similarly, if the question is find out the kinetic energy of the recoil electron or maximum kinetic energy of the recoil electron, we know that whenever we derive the formula, initially we have assumed that the electron is at rest. After this process, after the scattering, after the Compton effect, electron goes in a particular direction. That means then they have some velocity. Then the electron has some velocity. If it has some velocity, it must possess some kinetic energy. Now the question is, what is that kinetic energy and what is the maximum kinetic energy that can be? So this is our question. In numericals, this is a very common question. Find out the kinetic energy of the recoil electron. How will you do that? One way, first think, electron was at rest initially. Electron was at rest initially. Then what was the kinetic energy of the initial electron? Zero. Electron has no kinetic energy because it was at rest. After the scattering process, electron is moving in some direction. That means now it has some kinetic energy. Now it has some kinetic energy. Now rest mass of the electron remains same. Initially it has rest mass m naught c square. Now it has rest mass m naught c square. So it hasn't gained that kinetic energy from the rest mass energy. So from where the electron gets its kinetic energy. And if we can understand that, that also explains why in case of Compton effect, the energy, or better to say frequency, of the scattered photon decreases. We have observed frequency of the scattered photon decreases. What is the reason behind it? What is the reason behind the change in frequency or change in wavelength of the scattered photon? What is the reason? Now, once you observe that electron gains some kinetic energy, and there is only one way to gain it from the photon, because there are only two particles which are interacting with each other, electron and photon. Initially, the electron has no kinetic energy. Afterwards, it gets some kinetic energy. So there is only one way it can get it. It can get it from the photon. Initially, photon has energy h nu. After the scattering, it has energy h nu dash. So that change in energy of the photon gives rise to the energy of the electron. That means whenever photon interacts with the electron, photon loses some energy and electron gets that energy. Whenever photon interacts with the electron or the atom, the photon loses some of its energy and that electron or the atom gets that energy, and that energy becomes the kinetic energy of the electron of the atom. And since the photon loses some energy, as the photon loses some energy, its frequency must be reduced, because we know energy is proportional to frequency. So if energy is reduced, frequency must be reduced. And frequency and wavelength are inversely proportional. That means wavelength must be increased. That is the reason in Compton effect, the frequency must be decreased and wavelength must be increased, because photon loses some of its energy which the electron or the atom gets as its kinetic energy. Yeah? Therefore, the kinetic energy of the electron, is just estimated from the loss of energy of the photon. So h nu minus h nu dash, that is the loss of energy of the photon. H nu, I have written h nu dash, we have just estimated. This is the h nu dash, that means energy of the scattered photon. So if we put this value here, it will look like this. Now some simple calculation, we get kinetic energy as this. So this is the kinetic energy. Again, no need to remember it. I'm just showing you. You must do it once if this type of question comes. Now the point is, this is the expression of kinetic energy of the electron after the scattering. Now if the question is find out the maximum kinetic energy, how will you get the maximum kinetic energy? Maximum kinetic energy will occur when theta is 180 degree. If I put theta equals to 180 degree, that means cos theta will be minus 1. So this whole quantity will give you 2 value. So it will be twice h nu by m naught c square. Twice h nu by m naught c square. In the denominator also 1 plus twice h nu by m naught c square. That is the maximum kinetic energy of the recoil electron. That is the expression. Okay. If you have any query up to this, ask me.